Yes, sir. You are.
Yeah. Good evening, everyone.
Good evening, sir.
Yeah, good evening. Can you see the screen?
Yes, sir.
Yes. All right. We'll continue with what we have learned from the last class. We learned in detail the types of solids. Again, so solids are classified into 4 types. One is a molecular solid. In case of molecular solid, the particles, the constituent particles will be molecules. And there are 2 types of molecular solids. We learned non-polar and polar. Non-polar are molecular solids which is made of similar atoms. Example, hydrogen, iodine, carbon tetrachloride, etc. And they are soft, they are insulators, they don't conduct electricity, and they have very low melting point. Polar solids, heterodiatomic molecules. Polar solids are molecular solids which are made of heterodiatomic molecules like HCl, sulfur dioxide, etc. They will have dipole-dipole interaction, and they are again soft in nature. They are insulator and they have low melting point. And the third molecular solid, we learned hydrogen bonding molecular solids. Here, the particles are molecules. Example, water in solid state. And it's hard, it's an insulator, and it has low melting point. I am rushing through so that we can start with a new topic with the continuation of what we have learned in the last class. The second type of solids are ionic solids. In case of ionic solids, the particles are ions. Particles are ions when we say it can be a cation or it can be an anion. Cation ions are positively charged ions, anions are negatively charged ions. For an example, in sodium chloride, sodium will have positive charge and chlorine will have negative charge. So in ionic solids, particles are ions. This positive ions and negative ions, they will be held together by a strong electrostatic force of attraction. The bonding here is electrostatic force of attraction, or it's otherwise called as ionic bond. In simple words, it can be otherwise called as ionic bond. And these ionic solids are generally hard. They are insulator in solid state, but they are conductor in molten state or in aqueous state. Last class, I told you, if you take a beaker, in this beaker, if you take solid sodium chloride, and if I immerse 2 electrodes, positive electrode and negative electrode, which is connected to the power supply, switch on the power supply, and if I ask you to put a hand inside, when you put a hand inside, what happens? There won't be any shock. But the same to the salt, if you add water, it becomes aqueous NaCl. In aqueous NaCl, the sodium chloride will dissociate to form Na plus and Cl minus. So there will be a separation of what Na plus and Cl minus. The molecule will disassociate, separate to form Na plus and Cl minus. Now, when you pass current, what happens is Na plus will move towards the negative electrode and Cl minus will move towards positive electrode. The ion starts moving towards the respective electrodes. These ions are called as charge carriers. They are called as charge carriers. Since they carry charge, when you put a hand into it, what happens? You get a shock. That is why it says ionic solids are conductor in molten state or in aqueous state, and they have very high melting point. The melting point is very high. The third type of crystalline solids, what we've learned is metallic solids. In case of metallic solids, I told you what is kernels. Now, any metal for that matter is represented by letter M. This metal, when it loses electron, it gains a charge, positive charge. I don't know what is the valency of the metal. So if it loses n electron, the metal gains n plus charge. This n plus, metal n plus, will be called as kernels. The positive ion or the positive charge of the metal will be called as kernels. These positively charged metal ions will be surrounded by a sea of mobile electrons. Now, positive charged metal ions like this, if I represent positively charged metal ions like this, metal ions like this, M stands for metal ion, they're all positive, and I show you electrons like this, and I show you metals positive here also metal positive, here also metal positive, and we have electrons. So these are the representation. This is the representation of metallic solid. Metal ions are kernels, are surrounded by or immersed in sea of mobile electrons, sea of mobile electrons. When I say sea of mobile electrons, electrons will be moving. Therefore, we call it as a mobile electrons. C, when I say large number of mobile electrons, and the bonding between these metal kernels is a metallic bonding. Examples: iron, copper, or any other metal for that matter. And metallic solids are hard. They are good conductors of heat and electricity, and they have very high melting point. The next is covalent or a network solid. This covalent or network solid, in case of covalent or network solid, the particles are atoms. Now, covalent bonding is formed by sharing of electron. Now, for an example, if I take a covalent molecule like this, now if I take any covalent molecule, if I take X and if I take Y representation, X shares one electron and Y shares one electron. So sharing of electrons will be called as a covalent bond. A bond formed by sharing of electrons is called as covalent bonding. All right. So in case of network solids or covalent solid, the particles are atoms. These atoms are held together by covalent bonding. Silicon dioxide is an example. Sand, silica, SiO2 is silica. Sand is an example. Carbon, diamond is an example for a covalent crystal, and it is hard or soft. Covalent crystal may be hard or it may be soft. It is an insulator, or it also can be a conductor. It can be also a conductor. So covalent crystal can be either insulator or it can be a conductor, and melting point is very high. We will take an example and learn about covalent network or covalent crystal or network solids. Till here we had learned in the last class. So we'll have to continue further topic for our syllabus. Now, allotropic forms of carbon. Now, as we understood now, the covalent crystal example are diamond, graphite, and fullerene, Buckminster Fuller, or it is called as fullerene. So these are the examples for covalent crystals. Some of the examples for covalent crystals: allotropic forms of carbon, diamond, graphite, and fullerene. You should know that diamond is a non-conductor. It does not conduct electricity. But graphite and fullerene, these are conductors of electricity. That is what we learned here in the slide. Covalent crystal, it can be an insulator or it can be a conductor. So example, diamond is an insulator, graphite and fullerene both are conductors. So they are all covalent crystals. Now you can see the representation of diamond, graphite, and fullerene. Diamond, it has a cage-like structure. It has a complex cage-like structure. All these dark particles, what you can see, they are nothing but carbon. The next allotropic form of carbon is graphite. Now, the pencil lead is nothing but graphite. The pencil, when we write on the paper, it leaves a mark because the graphite is in the form of layers. You can see it's in the form of layers. Can you observe this? Students, yes or no? Ajay and others?
Yes,
Yeah,
Yes,
it is
sir.
in the form of layers. So therefore, when you write on a paper, it leaves a black mark. And this graphite, and here also you can see these particles, these are nothing but carbon. This graphite is also an example for a covalent crystal, and it is soft. Graphite is soft, and it is a conductor. So now the third allotropic form of carbon is fullerenes. Fullerenes is named based on a Buckminster Fuller. Buckminster is the name of a person. Buckminster Fuller is the name of a person who designed an architect like a soccer ball or a football. If you observe this carefully, you should have a hexagonal representation as well as a pentagon representation here. The soccer ball, the olden day soccer ball, you know that it will have white and black leathers patches. One will be like a hexagon, the other one will be like a pentagon. So Buckminster Fuller or Fullerenes, there are different forms. C60 we have, C70 we have. What does it mean? Fullerene made of 60 carbon atoms is called as C60. Fullerenes made of 70 carbon atoms will be called as C70. These fullerenes are used as a lubricants. They are used as a lubricants. And it can also be used in preparing carbon nanotubes and other nanoparticles, carbon nanoparticles using this. So these are the allotropic forms of carbon. Now, this is simple to be learned. So far what I've learned is simple. We'll have to learn the complex things now. The next is crystal lattice and unit cells. Crystal lattice and unit cell. Now, firstly, before we understand the term crystal lattice, we should know what is called as lattice points. Lattice points. Now, what is lattice points? Now, if I represent a cube like this for our understanding, if I represent a cube like this, we all know that a cube has 8 corners. A cube has 8 corners. In this 8 corners, if we have particles, I represent these particles by means of a dot like this. These particles which are represented by means of a dot is called as lattice points. The position of the particles in a crystal lattice is represented by means of a point, and those points are called as lattice points. Did you understand what I'm telling? What is lattice points? The position of the particles are represented by means of a dot, then it is called as what? A lattice points. Lattice point. Do you understand this?
Yes, sir.
Yes. Now,
Yes, sir.
I'll erase this. Erase this. Now, you just tell me if I place a point like this, randomly I'm placing a point like this. I think you can see the small points what I'm placing. Can you just tell me what is the structure of this, what kind of structure it will form? Randomly I'm not placing it in an order. Since I'm placing it in random positions, it will not form any structure. It will not give you any structure. No structure can be elucidated from this. No structural conclusion we can come. But if I represent a point like this, just observe this point very carefully and tell me what kind of structure can you elucidate, or what kind of structure can you conclude with these points? Just observe and tell me. Can you get any structure from these points?
Cube, sir.
It is a cube. Very good. It is a cube. If I draw like this, it becomes a cube. It becomes a cube. It becomes a cube. So, orderly arrangement of lattice points in 3 dimension is called as space lattice, or is called as crystal lattice. So you should know what is space lattice or what is crystal lattice. It is a regular array. Array means orderly arrangements. So when you arrange the lattice points in order in 3 dimension, it forms a space lattice or it forms a crystal lattice. This is a crystal lattice. It's an example for a crystal lattice. What we have drawn here, it's an example for a crystal lattice. So regular orderly arrangements of points. Points means it can be an atom or it can be an ion. It also can be a molecule. If it's molecular solid, it also can be a molecule. Orderly arrangement or regular arrangement of points in 3 dimension is commonly called as space lattice or crystal lattice. I hope you understood the definition of crystal lattice or space lattice. Yes or no?
Yes, sir.
Yes. Now,
Yes, sir.
the next is an important definition for your regular exams. Now, if you know bricks are used to construct a wall or construct a house. Maybe we'll assume that bricks are used to construct a wall. Now, if I place a brick like this somewhere, it is also randomly placed. It is also randomly placed. Can a wall be formed from here?
No,
You
sir.
cannot have a wall here because it is not placed in order. It is not placed in order. Now, if we place the bricks in order, if I place the bricks in order like this, all right, like this, then you can construct a wall. You can keep on extending this. You can construct a wall. Now, if I have to construct a crystal, if we have to construct a crystal, we need to have something called as unit cell. We need to understand something called as unit cell. What is this unit cell? The smallest repeating unit in a crystal is called as unit cell. What is the unit cell definition? The smallest repeating unit in a crystal is called as a unit cell. Now, in order to construct a wall, what is the repeating unit here? The smallest repeating unit here is what? A brick. So when brick is placed in order repeatedly, then you get a wall. Likewise, if a unit cell is placed in order repeatedly, we can get a crystal. A cube, what we represented, is not a complete crystal. Many number of cubes will join and then forms the crystal. This is the smallest unit. This cube is the smallest unit. The smallest unit, when we orderly place it, then the structure becomes bigger and bigger in size, and then you get a crystal. The smallest repeating unit in a crystal is called as a unit cell. Did you understand what I'm telling? What is units? Did you follow this?
Yes, sir.
We learned three definitions now. What are the three definitions now? One is lattice point. One is lattice point. The other one is space lattice. The third one is unit cell. So lattice points are nothing but the position of the particles are represented by means of a point, and those points are called as lattice points. When these lattice points are arranged in order in 3 dimensions, then we call that as a space lattice or a crystal lattice. And the smallest repeating unit in a crystal is called as a unit cell. Now, see here, the definition is very clear here. The unit cell is obtained by joining the lattice points. So cube was obtained by joining the 8 points. So a cube is an example for a unit cell, I told you. So many number of cubes, when repeatedly arranged, then you get what? A crystal. A unit cell is obtained by joining the lattice point. The choice of lattice point to draw a unit cell is made on the basis of external geometry of the crystal and symmetry of the crystal. External geometry and symmetry of the crystal we are going to learn now in detail. Now observe this. Now observe this. This is an x-axis. This should be written as, this is an axis maybe. Okay, this is x and y and z, or however it is. Okay, now this is a cube. This is a cube. Maybe we'll mark this as x, and this will mark it as y, and this will mark it as z. Now, this is a cube. The length of the cube is marked as a. The width of the cube is marked by b, and the height of the cube is marked by c. All right. See, sometimes what happens is in a cube, a can be equal to b, b can be equal to c. Here, looking at the diagram, you cannot conclude a, b, and c are equal because a looks lengthier compared to b and c. So sometimes a can be equal to b, b can be equal to c. All that we will learn in detail now. A cube has 3 axes, x, y, and z. Okay, the length is represented by letter a, the width is represented by letter b, and the height is represented by letter c. This is very important for you to understand. See the angle, the angle between x and y is represented by beta. The angle between x and y is represented by beta. The angle between y and z is represented as alpha. Don't get confused. This is x, this is y, and this is Z. The angle between Y and Z is alpha. Likewise, the angle between Z and X is represented by gamma. Do not get confused. So a cube has 3 axes and it has edge length, width, as well as height. And it also has 3 angles, alpha, beta, and gamma. So the angle between X and Y is beta, Y and Z is alpha. Likewise, X and Z is gamma. So bond angles, you should remember. Is it clear with this representation?
Yes, sir.
Yes. Now, types of symmetry. Now, what is this types of symmetry? Symmetry means similarity. Now, for an example, if I draw a circle like this, and if I draw an imaginary line like this, now tell me this imaginary line does this imaginary line divide the circle into 2 equal halves?
Yes, sir.
Yes. So whenever a crystal or whenever any substance can be divided, take a triangle like this. If I draw an imaginary line here, this imaginary line also divides the molecule, the triangle into 2 equal halves. So this is we can say this triangle also contains what? Plane of symmetry. Now, plane of symmetry is an imaginary line which divides a crystal into 2 equal halves. Now, if you observe this, it's a simple cube. We are talking only with respect to a simple cube. Now, you can see, now, if I represent a square like this, if I draw a line like this line divides the square into 2 equal halves. Now, here, it equal halves. Therefore, we can symmetry. This is called as common plane of symmetry or general plane of symmetry. Now, likewise, you can see, observe this cube. This cube is divided here, rectangular, not from the center, from top to the bottom like this. All right. So this division or this portion which divides the cube into 2 equal halves will be called as rectangular plane of symmetry. Likewise, we have diagonal plane of symmetry from one corner to the other corner, from this corner to the other corner. It's not clear in that picture. So if we draw this corner to the other corner, and then we can divide the cube also into 2 equal halves, then this, we say, this cube has diagonal plane of symmetry. So plane of symmetry is nothing but an imaginary line which can divide the particles or divide a crystal into 2 equal halves. Now, a cube has 3 types of plane of symmetry. What are the 3 types of plane of symmetry? One is a general common plane of symmetry, which divides the molecule into 2 equal halves. The next is a rectangular plane of symmetry. Third is diagonal plane of symmetry. You all know what is diagonal plane of symmetry, yes or no?
Yes, sir.
Now, when I was talking about the circle and when I was talking about the triangle and the square, I told you imaginary line. But in case of a cube, it is an imaginary plane. It is an imaginary plane. An imaginary plane which divides the cube or the crystal into 2 equal halves will be called as 2 equal halves is called as plane of symmetry. No problem with this?
No problem.
Yes. All right. Continuation of this. See, the solids chapter is a little tough. So you need to concentrate on this. You need to have a lot of imagination. You should try to visualize what I'm trying to talk about, because I do not have a 3D model to represent. No, it's difficult. Anyways, now axis of symmetry. Now, what is this axis of symmetry? Now, this axis of symmetry can be defined as imaginary line about which the crystal may be rotated so that it presents the same appearance. More than once. More than once. Incomplete rotation through 360 degrees. We'll understand this. Now, what is this axis of symmetry? Axis of symmetry is an imaginary line about which the crystal may be rotated so that it presents the same appearance more than once in complete rotation through 360 degrees Celsius. Now, if you know that if I draw a straight line, we know that the angle is 180 degrees. 180 degrees. If I draw a circle, and the circle can be rotated completely 360 degrees. So the bond angle can be called as 360, yes or no? The mathematical terminology, I don't know. For a straight line, the bond angle is 180 degrees, but for a circle, we can rotate. If I hold a paper which is in a circle, the form of a circle, and I can rotate it to 360 degrees, yes or no?
Yes, sir.
Yes. Now, this axis of symmetry is the imaginary line about which the crystal may be rotated so that it presents the same appearance more than once in a complete rotation through 360 degrees. Now, just observe this. This all three are cubes. This representations are cubes. Now, if you rotate a cube from this position, it's fourfold symmetry. Fourfold symmetry. What do you mean by that fourfold symmetry? For every 90 degrees, the cube will appear what? Same. So if you rotate for 90 degree, if you rotate once for 90 degree, the cube will appear as it is as it is visible now. Next, you rotate for another 90 degrees, it will again appear the same. Likewise, if you rotate for another 90 degrees, 4 times if you rotate 90 degrees, what happens is this cube will look similar as it was initial. Therefore, we call that as fourfold symmetry. Did you understand what it means? Fourfold symmetry means?
Yes, sir.
Yes. Now tell me, if you have understood, you tell me what is threefold symmetry and twofold symmetry. Someone tell me. You can see the differences in the cube. What do you mean by threefold symmetry? What is the bond angle? What's the rotation here? If we rotate 120 degrees Celsius 3 times, 120 degrees 3 times, totally it's again what? 360. So if you rotate 120 degrees from 120 degrees, this cube will appear same. Likewise, 3 times we can rotate 120 plus 120 plus 120. So on one complete 360 degree rotation, this cube will appear like this. How many times? 3 times. Therefore, it is called as threefold symmetry. Yes, students. Yes.
Yes, sir.
Yes. Now, twofold symmetry means what? The bond angle should be how much? 180
180 degrees.
So if you rotate 180 degrees, the crystal will remain, it will look similar as it was initial. So 2 times you can rotate 180 degrees. Therefore, the crystal will appear twice similar on complete rotation of 360 degrees. This is called as axis of symmetry. So axis of symmetry is an imaginary line. Plane of symmetry is an imaginary plane. Let's remember that. So imaginary plane, we have plane of symmetry, rectangular plane of symmetry, diagonal plane of symmetry, and axis of symmetry. We have learned fourfold axis, threefold axis, twofold axis. We have one more, a sixfold axis also. Sixfold axis. When you say six-fold axis, so each time if you rotate 60 degrees, what happens? The crystal will appear same. So those kind of axis of symmetry is called a six-fold axis. The third, what we have is center of symmetry. It's a point in a crystal that any line drawn through it intersect the surface of the crystal at equal distance. So the definition is it's a point in the crystal. Point in the crystal that any line drawn through it intersects the surface of the crystal at equal distance on either side. Now they've represented a dot here. Just imagine this is a roof and this is the floor. If I draw the line here, the distance between the roof and the floor will be what? Same. Or if I draw the line to this this face and this face, the distance between the two faces will be what? Same. So therefore, this point is called as center of symmetry in a cubic crystal. What is center of symmetry? It's a point in the crystal that any line drawn through it intersects the surface of the crystal at equal distance on either side. I've shown two directions here. So that's called as a center of symmetry. That's called as center of symmetry. Clear with this?
Yes, sir.
Yes. Now I don't know whether to go for this or okay. Now there are four types of unit cells. You know what is unit cell? The smallest repeating unit in a crystal is called as a unit cell. There are four types of unit cells. They are called as primitive or simple cubic. Simple cubic. And next, what we have is body-centered cubic, BCC, face-centered cubic, and side-centered cubic. The side-centered cubic is also called as edge-centered. Edge-centered. We will understand the simple cubic, body-centered cubic, face-centered cubic, and side-centered cubic crystals now. Now, in case of a simple cubic, please understand this. Please understand, we'll have to work some numericals based on this. Based on this, there will be a question in your competitive exam, so you should be paying more attention when I'm teaching you this. Now, in case of a simple cube, the particles will be present only at the corners of the cube. Whenever the particles are present only at the corners of the cube, then those kind of cubic crystal or those kind of unit cells are called as simple cubic. They are called as what? Simple cubic. You can understand this. The cube has 8 corners. So in the 8 corners, there are particles. So since there are particles placed in the 8 corners, only this representation will be called as a simple cube. Atoms are arranged only at the corners of the unit cell. Particles, I'm using the term particles. It can be ions also. That's why I'm using the term particles. So atoms or ions, when they're arranged at only the corners of the unit cell, then they are called as a simple cubic cell, a simple cubic unit cell. Followed? Followed?
Yes, sir.
Now,
Yes, sir.
for a body-centered cubic lattice, now this is a representation of a simple cube. Now, if I want a body-centered cubic lattice, see, I am placing at the center of the cube one more particle here. The red color particle is present at the center of the cube. The red represents a particle which is present at the center of the. Now, I don't know. So far, we have been talking about the topic. Now, you tell me, in case of simple cube, how many number of lattice points we have in case of simple cube? If you're following me, you should be in a position to answer. In case of simple cube, how many lattice points?
8, sir.
8.
8.
Huh?
Eight.
Very good, very good. In case of body-centered cubic lattice?
So 9.
9.
Very good.
9.
So corners, you have the particles as well as at the center. Just imagine the room where you're sitting as a cube, because any room for that matter will have 8 corners. And in that corners, you assume there are particles. Likewise, there is a fan which is hung at the center. And that fan is present at the center of the room. And that you assume this red particle is nothing but a fan which is present at the center. So those kind of cubic unit cell are called as body-centered cubic. It's represented as BCC. So atoms are arranged at the corners and at the center of the unit cell. When the atoms are arranged at the corner and the center of the unit cell, they are called as body-centered cubic lattice or cubic system. Now, coming to the next, face-centered. I'll try to draw neatly. Let's see how it comes. You should understand this representation also. This is a simple cube, what I'm drawing. Now, particles are present at the corner. Now you tell me, look, now you're sitting in your room, look at, observe your room and tell me how many faces a room has. How many faces a room has? How many faces a room? Huh?
6.
6 faces. Okay. One is facing you, one is behind you, one towards left, one towards right, one on the top, one at the bottom. Yes or no? 6 faces?
Yes, sir.
Yes. Now, if the particles are present not only at the corner, but at the center of each face. So this is the face on the top, like roof. This is the face which is at the bottom. This is the face which is on the left-hand side. This is the face which is on the right-hand side to you. You have to imagine. This is the face which is facing you, and this is the face which is behind you. All right, don't get confused here. This dot is for the face which is behind you, and this dot particle bottom facing is for the face which is facing towards you, or which is closer to you. So what is the number of lattice points this face-centered cubic lattice will have? What's the number of lattice points? What's the number of lattice points this face-centered cube has?
14.
14. That is 8 plus 6. 8 at the corners and 6 at each face. So therefore 14. So face-centered cubic lattice, atoms are arranged at the corners and at the center of each face. So these 3 are for our prime importance for your exams and the regular classes. Now this edge-centered or side-centered, we do not learn in our syllabus, but we'll try to understand. Atoms are arranged center of only one set of face in addition to the atoms at the corner of the unit cell. Now, what do you mean by that? This is a unit cell. So this unit cell, particles are placed in the corners like this. And if particles are placed at the edge, see, maybe here like this. See, it clearly says atoms are arranged at the center of one set of face. So if the atoms are placed here in the edges, then they are also called as edge-centered unit cell, or it is also called as side-centered unit cell. We do not talk about edge-centered unit cell in our syllabus. This tabular column, what is being projected, you should know this. You should memorize this for your competitive exams. Now, what is there? What is that? What is this? Now, I told you what is ABC. When I was discussing,
Sides.
yeah, I clearly said A is the length, B is the width, and excuse me, C is the height. And I clearly told us what is alpha, beta, gamma. You should remember that. The angle between X and Y is
Angle.
beta. Yeah. The angle between Y and Z is alpha, and the angle between X and Z is gamma. So based on this you should memorize and remember. Now, when we see when you arrange points in any form, you wish, and join those points, okay, you will find 7 types of crystals. So how many types of crystal systems we have? We have only 7 types of crystal systems. Those 7 types of crystal systems are represented here. One is cubic crystal. The second one is tetragonal. Third is orthorhombic. Fourth is rhombohedral. Fifth is hexagonal. Sixth is monoclinic, and seventh is triclinic. So we'll have 7 types of crystal systems: cubic crystal system, tetragonal crystal system, orthorhombic crystal system, rhombohedral, all that. Now, much complex we'll be learning further. Now you should remember, in a simple cube, A is equal to B is equal to C. What do you mean by A is equal to B is equal to C? Length is equal to breadth is equal to height, or length is equal to width is equal to height. A is equal to B is equal to C. And also alpha is equal to beta is equal to gamma, and gamma is equal to 90. 90 degrees. A unit cell is called as a simple cube, and it has number of lattice. It has this lattice we will learn in the next slide. It's called it's named by Augustus Brevius. It's called as Brevius lattice. A simple cube has 3 Brevius lattice. What is the 3 Brevius lattice? A cubic system has it. It has simple cube. Another one is body-centered cubic lattice. The third one is face-centered. You understood what is a simple cube. You understood what is body-centered cube, and also you understood what is face-centered cube. So these 3 are called as Brevius lattices. The next slide we will be learning about Brevius lattices in detail, possibly. Okay. Now you should remember, in a cube, alpha A is equal to B is equal to C. Edge length is equal to width is equal to height, and alpha is equal to beta is equal to gamma, that's equal to 90 degrees. In case of a tetragonal system, alpha A is equal to B, but B is not equal to C. But alpha, beta, gamma, all are 90. I'll go to the next slide directly here. Yeah, this will be better, I feel. This slide will give you a clear understanding, because pictures are represented here. Right? So in case of cube, as we discussed, A is equal to B is equal to C. Likewise, alpha is equal to beta is equal to 90 degrees. In case of tetragonal, A, edge length and the width is same, but the height is different. That's why they've written A is equal to B, but A and B is not equal to C. But the angle, alpha, beta, gamma, all are 90 degrees. All are 90 degrees. These are the 7 crystal system what we're discussing. The next is monoclinic. In case of monoclinic, A is not equal to B, B is not equal to C. Length, width, and height are not equal. But you can see alpha and gamma is equal to 90. Alpha and gamma is equal to 90, but beta is not equal to 90. Okay, you know what is alpha, what is beta. The bond angle between X and Y axis is called as beta. Remember that. So alpha and gamma is equal to 90, but beta is not equal to 90. The fourth one is orthorhombic crystal. A is not equal to B, B is not equal to C, but alpha is equal to beta, beta is equal to gamma, and all the 3 are equal to 90 degrees. Coming to the next crystal system, triclinic. In case of triclinic, A is equal to B is equal to C. Length, width, and height is equal, but alpha is not equal to beta, beta is not equal to gamma, and all the 3 are not equal to 90 degrees. Different bond angles it will have. Those kind of crystal system is called as triclinic. And next we have is hexagonal. In case of hexagonal crystal system, A is equal to B, but B is not equal to C. And alpha is equal to beta is equal to 90. It is confusing. It's confusing compared to monoclinic. See, in case of tetragonal, A is equal to B, but B is not equal to C. Here also same. With respect to the length, width, and height, same factor. But the bond angle in case of tetragonal, A, alpha, beta, and gamma 90. Here, alpha and beta is 90, but gamma is 120. That difference you should remember. All right. The last type of crystal system, what we have is called as trigonal. In case of trigonal, A is equal to B is equal to C, and alpha, beta, gamma, all the bond angles are not equal to 90 degrees. Just keep observing the crystal system and make a note of it. And this is important for learning. Any clarifications in this? If you can ask me quickly.
Sir, in triclinic, all the sides are also will be not equal.
Yeah, it looks like not equal here, but it is A is equal to B is equal to C. In case of triclinic, the lengths are length, height, and width are same. You can see in the slide also in triclinic. Oh, there's a mistake.
Not equal, sir.
Yeah, it's not equal. This mention it as equal. Okay. The pictorial representation is right, but the printing here is not right. Maybe A is not equal to B, B is not equal to C. Okay, correct. You're right. Thank you. Anything else? How many are there in the class today? All right. Any clarifications? We'll continue with Bravest lattice now. Any clarifications? We'll continue.
Yes, sir.
Yeah, one slide I'll finish. Oh, it'll take time, you know. All right. Anyways, one slide we'll finish up. Bravius in 1848 showed from geometrical consideration that there can be only 14 different ways in which similar points can be arranged. Thus, there can be only 14 different space lattice. A space lattice or crystal lattice we learned in the beginning. 14 different crystal structures we can have. And they are all known as Bravest lattice. So here also I represented. Here I represented simple cube, body centered and face centered. A cube can be 3 Bravest lattices. That is what he says. So if you arrange the points in different ways, possibly you will get only 14 types of crystal structures. And those kind of crystal structures are named by on a scientist named Bravest, Augustus Bravest. So it's called as Bravest lattice. You have only 7 types of crystal system, but we have 14 types of Bravest lattice. Remember, 7 types of crystal system. 7 types of crystal system and 14 types of Bravest lattice. 14 types of Bravest lattice. Now, the first crystal system, I'm rushing through this because we have already learned. First crystal system is cubic. In case of cubic, the Bravest lattice, 3 types of Bravest lattice you can have. Simple cube, body-centered cube, and also face-centered cube. This we discussed. Now, example for a simple a cubic crystal, sodium chloride, copper, zinc sulfide. See, metal also can have cubic crystals, metals, pure metals. There were examples, a few of the examples are given here, NaCl, copper, and zinc sulfide. Now, tetragonal crystal system, it has only 2. It has primitive, simple cube, as well as body-centered cube. Example, white tin, tin dioxide, titanium dioxide, calcium sulfate. Orthorhombic crystal, it has 4 Bravest lattice. It has simple cube, it has body-centered cube, body-centered, it has face-centered, as well as it has edge-centered, or it's called as end-centered. So it has 4 Bravest lattices. Orthorhombic crystal system has 4 Bravest lattices. Example, rhombic sulfur, barium sulfate, potassium nitrate. And the hexagonal crystal system, it has only 1 Bravest lattice, simple cubic Bravest lattice. Example, graphite, zinc oxide, cadmium sulfide. The next, rhombohedral, it also has only 1 Bravais lattice, simple cubic, simple cubic or primitive lattice, calcium carbide, calcium carbonate. See, this calcium carbonate is amorphous. In your labs, your teachers would have given you calcium carbonate for analysis, which is in amorphous state. Calcium carbonate can also be in the crystalline state. Crystalline state of calcium carbonate is called as calcite. This calcite has a rhombohedral crystal structure, and it has only one Bravais lattice, primitive Bravais lattice. Next is monoclinic. It has primitive end centered. The example is sulfur. And triclinic, it has only primitive. So example is phosphorus acid, hydrated copper sulfate. These are the examples for triclinic primitive crystals. So if you count, it has 3. Cube has 3. This is 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So totally, you can have 14 Bravais lattices. All right. So in case of your NEET or your regular class, you will have to concentrate only on a cube. You are not concentrating on other crystal systems. But you should know how many crystal systems are there. 7 crystal systems, and how many Bravais lattices are there. You should know that you have 14 Bravais lattices. No doubt with that question. Number of crystal system is 7 and number of Bravais lattices 14. But otherwise, in our syllabus, we have only a cube which you have to learn in detail. Possibly we will, this is a pictorial representation. See, a cube has a simple cube. It has only corners, and you can see there's a particle at the center and face centered 6 faces, all that they have represented for each crystal systems. Okay, you can just observe this carefully so that you will get to know. So as I was telling you, you should remember the number of crystal system, it is 7, and number of Bravais lattice is 14, and we'll have to concentrate more on the cubic system in the next class. You have any clarifications, you can ask me now.
No, sir, no clarity.
Yeah. Anybody? Mahendran sir, can I stop now?
Yes, sir. Yeah. Thank you.
Okay, sir. Okay, sir. I can end the meeting, no, sir?
Yes, you can make. Yes, you can do.
Yeah, I can end the meeting. Okay, sir. Thank you.
Yeah, thank you.